So I'm excited to introduce our next speaker, Ariane Prabowo, who is a postdoctoral researcher at the University of New South Wales. His project involves the application of machine learning in the energy industry to enhance sustainability. This is his second BuildSys conference, and we're super excited to have him back. The floor is yours.
Thank you very much. My name is Ariane. You might recognize the last author. Professor Flora Salim was presenting yesterday about the LLM work, and the third author, Hao Shui, was the first author for the paper. And I'm here working on the same, the extended form of the data set. So you might be interested as well, I hope. So the questions that we have in mind, so the task at hand is energy load forecasting. And this is a typical, this is an example of 2 weeks of energy use in a building. Sorry, just give me a second. Yep. And this is an extreme event such as COVID-19 can change the energy use pattern, such as shown before lockdown and after lockdown. There's a huge change in distribution. So the question is, what is the best way to adapt to such changes? So this is our data set. We have 13 building complexes, and this means it's a high spatial granularity than what is common in the literature, which is usually at the good substation level. This is in practically building levels. It's actually a number of buildings combined, so you can assume they are mixed use to protect the privacy of each building. And more interestingly, all of them are from my home city-ish, Melbourne, Australia, which is a city famous for experiencing the longest and strictest COVID lockdown in the world. So here's a picture from there. And the data set is also very diverse. So there are 13 building complexes, and the durations ranges from like 1.5 years to 3 years. But if you were to look at the mean and median columns, you for example, compare building 12 and 13, the mean for building 13 is about 300 times larger than building 12. So there's a huge variety. So there's a huge variety of distribution here, and you can assume all of them are some sort of mixed use. And not only there's diversity in magnitude, there's also a diversity in distributions, as you can see. And the red region on the right-hand side are the lockdowns. And we augment this energy use data set, electricity use data set, with a mobility data set. There are mobility sensors installed by the city of Melbourne. It does not capture images to protect privacy. No images or videos to protect privacy, so that's nice. And the best thing about this is it's publicly available. So if you go to my paper, there's a URL, and then you can download the data up until today. So it's a very nice data set to have. To do our benchmarking, we compare 13 baseline methods all the way from something very naive, for example, literally copy last day. I hope that's explanatory. We just assume it's the same value as yesterday, it's the same value as an hour before. Also typical machine learning like random forest, XGBoost, and vector autoregression, which is basically just linear regression, all the way to various deep learning and also a subset of machine learning like online learning and continual learning. So 13 baseline methods in total. We also want to compare different features. The typical ones are energy use, past energy use, hour of day, day of week, but also another one like temperature, and also mobility as mentioned before, and the combinations, interactions of these features. And to do that, since we want to ask a question, how does this different method and features combination compares at different time? So we divide the time into 5 different time period: pre-lockdown, the first lockdown, the first inter-lockdown. So we managed to get to 0 or very close to 0. So we open up for a while, that didn't last long. There's a second lockdown, and there's and there are even more. But our data set stops at at the end of 2020. And since there are a huge combinations, all possible combinations between methods and feature. This is so just for one single building, we have all of these different combinations, and this is sorted from best to last. Since that's a lot, let's aggregate them, right? So this is for every single building, and this is just the best method, right? So for example, we're just literally taking just the first line, just the best one. And this is the result. The winner is FSNet. It's a continual. The family, it falls under a continual deep learning method. It shows up number 1 in 12 out of 13. And one thing that we learned is that the data is very nice. It seems to be stable throughout all time period. Very, very stable. So if something works very well in the pre-lockdown, usually it also works well during the other time period. So I think that's a very nice takeaway in this benchmarking exercise. Next point, mobility. Yes, mobility improves in 5 out of 13, which is surprisingly even more than temperature, which is only improved in 4 out of 13. So you can think mobility is on par with a temperature. All right. How much better is FSNet compared to the second best? So we want to compare. So this is we go and analyze the methods a little bit more to see how much is the improvement between the best and then the second best when it comes to method. What I find, so it's actually quite modest, right? It ranges from like 40%. The only thing that's negative here is only here, 3%, right? So it means if whatever's number 1, it will stay as number 1 for the rest of the period. So it's a very, very modest improvement in the region between 10 to 20 to 30%. And what I find surprising personally, and I hope you as well, is that this var plus OL and that is adding online learning on just simple linear regression. And the idea of online learning is that you don't stop the machine learning training at any point. You keep on updating the weights as we go, as we get new data. So even then, simple linear regression, if we add online learning, actually performs surprisingly well. So that's surprising to me. And so this is when we go and analyze the mobility dataset. Again, it seems that when mobility is improving before lockdown, it stays. It's also very helpful even in the other time period, right? So the only exception seems to be in this dataset and in this time period, where it's like harms just a little tiny bit, like 0.5%. But and we can expect improvement ranging from a modest like 3-4% to 12 and 19%. Yeah. So yeah, that's nice, and that's it. This is the conclusion. As I shared before, for every single data set, we have a very huge combinations of all methods and features and feature set. We don't put everything in the paper, but I put everything on the GitHub. We cannot release the data set, but at least I want to be as transparent and release as much of the experimental artifacts as possible. And yeah, thank you very much.
Thank you so much for the great talk. Questions from the audience?
First, thanks for the great presentation. I want to ask you a question about the electrical energy consumption data set. Was it taken from residential households?
So it's all mixed use. This is all in. Do I have the map? I don't have the map. So it's all mixed use. They're all from Melbourne CBD, and that means I don't think there are any like small houses. If there's any, they are definitely residential, but it will be in the form of like apartments. But you can assume there are mixed use. Some are education, some are retail, some are office buildings.
Because in the line chart that was in the first couple of slides, we see a decline in the energy consumption after the COVID, which is not expected for households because people stayed more in the houses during the COVID lockdown and they use electronic entertainment. Maybe the percentage of the non-residential buildings are high in that data set.
Yeah, I can. Well, I cannot say which building this exactly is, but in general, the data sets are at least within the same building block, within the same block in the CBD. So yeah, and being in the CBD in the downtown also means there are more non-residential buildings in general. Yeah.
So we have a diverse building.
Exactly, very diverse.
Thanks.
Thank you.
We'll go over there, then here.
Hey, over here, thank you for your presentation. Could you comment on how much effort you put into the modeling? Because obviously, like a simple model is easier to train, easier to tune. Let's call it like this. So could you just comment on this? How much effort you put, for example, into a long short term like LSTM or one of those more sophisticated models in order to perform well?
Sure. I think I finished the whole thing in like few months. So to be fair, I'm coming from a machine learning background, so I'm used to running this set of experiments. I guess that helps. And yeah, I think I didn't mention it, but in the paper I also like standardized everything beforehand. I know exactly what are the criteria, hyperparameters to search. So there's no, it's not like developing a new model where I have to go back and then fine tune things. Yeah.
Okay, perfect. So basically, you tuned each of those models. None of them is off the shelf, and it's comparable.
Yes, so it's off the shelf-ish in terms of I use off the shelf algorithms, and I don't do my own implementation, and I also do the of the recommended hyperparameter range. Yeah.
Perfect.
Yeah.
Thank you.
Yeah.
And we have our last question over here.
Hello, thank you very much. Great talk. It's great to see such a wide selection of the baseline methods and the correct and the proper evaluation of them. Yeah, my question was about the online learning. Yeah, it seems like you included the models that use the online learning. Can you elaborate a little bit how it works? For example, in the case of the linear regression, is linear regression retrained then at every new instance, like a new sample, and or other way to adjust it or like retune in some manner? And do you use a fixed origin or a sliding, like rolling origin for the training data, like a look back period? Is it sliding window or is it a fixed origin and then the window keeps expanding?
I see. Okay. So the experimental setup, in the interest of time, so these are the distribution of sensors. I forgot I put it at the back. This is the experimental setup. So I use a sliding observation window. Basically, the idea is we look 24 hours beforehand in terms of and past passages of energy, temperature, mobility, and we're forecasting 24 hours ahead of energy. The metrics is in MAE, and so some, and this is where we have training, we have validation. Yeah, this is the details of the setup. But with the idea of online learning is basically we do not have this is it, right? Usually in machine learning and deep learning, we train and then we freeze all of the weight for the rest, right? But with online learning, we do not freeze the weight. As new data comes in, we basically do one step of gradient descent as new data comes in. That's roughly how online learning works. And the best method, which is a family of continual learning, the way it works is basically instead of updating all of the weights, there's some mechanism to decide when to update the weights and like only a subset of the weights are being updated. So in short, yeah, I hope that answered your questions. Thank you.
Thank you, Ariane.